This is Babitha, working as Assistant Professor in the Department of ECE in Institute of Aeronautical Engineering. In this session, I'm going to discuss about different definitions as well as terminologies which we are going to utilize in the operational amplifier module. So in the case of operational amplifier, we're going to discuss the ideal operational amplifier as well as practical operational amplifier, and what are the characteristics of ideal operational amplifier as well as what are the characteristics of the practical operational amplifier. So while coming to the characteristics of the operational amplifier, we are having output offset voltage, input bias current, input offset current, slew rate, and gain bandwidth product. So these all are the characteristics of the operational amplifier. So these are the some predetermined values in the case of ideal one, that may be almost 0 or infinite. Those values may be either 0 or infinite in the ideal case, but in the practical case we may get those values are either low or high values. We may not reach to either 0 or infinity in the case of practical operational amplifier. And next we're going to discuss about different modes of operations of the operational amplifier. So here it will operate in 3 modes, that is inverting mode, non-inverting mode as well as differential mode. In these 3 modes it can able to operate here. And next we're going to discuss the applications of the operational amplifier, in that about differentiator, integrator, or the integrator, differentiator are the mathematical applications or mathematical operations performed by the operational amplifier, and along with that some waveform generators also we can be able to design by using operational amplifier. Those are square wave generator and triangular wave generator. So the terms which are going to utilize in these characteristics and modes as well as in the applications of operational amplifier we are going to see in this session. So the first one is define an operational amplifier. So here operational amplifier is a direct coupled amplifier, and it will provide very high gain compared to the normal either single stage amplifiers or multi-stage amplifiers. So if we compare the gain in the multi-stage as well as in the single stage amplifiers, the gain provided by the operational amplifier is very high, and it consists of one or more number of differential amplifiers. So we can able to implement the operational amplifier by using the different differential amplifier configurations. So we can say in the case of operational amplifier, we can indicate with a triangle, and it is having 2 inputs. One is the inverting input and one is the non-inverting input, and we will get the output here. So this is some B2 or B1 here. So why in the operational amplifier we are having 2 input terminals means the internal stages of operational amplifier consist of differential amplifier. So for any differential amplifier we will take 2 input signals. So the function of the differential amplifier is to amplify the difference of the applied input voltages across the 2 input terminals. So that's why, because of that reason, in the case of operational amplifier also we are having 2 input terminals. So these operational amplifiers, if we along with this operational amplifier, if we choose some external components so that it can able to perform different mathematical operations. Suppose to perform the integration by using the resistance and capacitors along with the operational amplifier, we can able to implement the integrator circuit as well as the differentiator circuit. And next mention the characteristics of an ideal operational amplifier. So while coming to the characteristics of ideal operational amplifier, it will provide the voltage gain is infinite. In the ideal case it is infinite, and the input impedance provided by the ideal op-amp is also infinity, and the output impedance from the amplifier is 0, and the bandwidth also infinity in the ideal case, and it will provide 0 offset voltage. That is nothing but what, whenever both the inputs for the operational amplifier are 0. That is nothing but the differential voltage is 0. Vd is nothing but V1 minus V2. If both the voltages are 0 means the differential voltage is also 0. So the differential voltage across the input of the operational amplifier is 0 means the output voltage must be also 0 here. So if it is not 0, even though both the inputs are 0 means we have to add some external bias across the two input terminals of the operational amplifier in order to make this voltage as 0 here. So that particular voltage we are calling it as 0 offset voltage or 0 offset current. That may be the voltage or current here, but we can call it as the offset or 0 offset. So these values in the case of ideal operational amplifier, but in the practical operational amplifier we may not reach these particular values. Here in the practical case, voltage gain we may reach some high extent, and here also it is high, input impedance is high and the output impedance is low, and the bandwidth also we will get it as high, and it is low value, offset voltage as low value. Along with this, it will also provide the infinite slew rate here. Slew rate is nothing but a rate of change of output voltage with respect to the time, or rate of change of the output voltage with respect to the applied input signals. So that is also we will get infinite in the case of ideal operational amplifier. And it is also provide the CMR or common mode rejection ratio also infinite in the case of ideal operational amplifier. And next, what happens when the common terminals of positive voltage and negative voltage sources is not grounded here? Here, in the case of operational amplifier, we are providing both the supplies plus VCC, that is nothing but plus V, and minus VE, that is nothing but minus V. So one terminal of, here it is plus VCC means the positive terminal of the battery is connected to this operational amplifier, and here the negative terminal should be grounded. And in this case, the negative terminal of the battery is connected to the operational amplifier and the positive terminal should be grounded. So the other terminals of both the supplies must be grounded here. If we are not grounding the other terminals of the power supplies, it may cause damage to device. It may burn the IC here. It is the 741 operational amplifier IC here. So it will cause damage as well as the same voltage is applied as 2 times for the circuit here. And next, define input offset voltage. So input offset voltage is nothing but it is the small voltage applied to the input terminals of the operational amplifier to make the output voltage as 0 here. When and on what condition it may take it as 0 means whenever both the inputs are zeros are grounded here. That is nothing but if we are connecting both the terminals of the operational amplifier are ground means the output must be 0 here. But in some cases, in some practical applications, we may not reach this value as 0. So to make it this value as 0, we are applying some external voltage. That external voltage we are calling it as input offset voltage, VIOS. We are indicating here it as VIOS. So this VIOS across 2 input terminals we will apply to make this voltage as 0 whenever both the inputs are grounded or 0 here. In the ideal case, this value must be 0, but in the practical case, we need to provide some value here. And next, define input offset current. So input offset current is nothing but that is the difference between the 2 currents which are entering into the inverting terminal as well as non-inverting terminal of the operational amplifier. It is nothing but here in the inverting terminal some current is flowing, that is we are taking here it as IB2, and through the non-inverting terminal some current is flowing, we are taking here it as IB1. So this input offset current we are indicating with IIOS. IIOS means input offset, here it is. That is the difference of IB1 minus IB2. Okay, so this is the algebraic difference between the two currents which are flowing in the two input terminals of the operational amplifier. And next, define CMRR of an operational amplifier. So here CMRR is nothing but a common mode rejection ratio. So here the sensitivity of the operational amplifier is to a different signal as compared to a common mode signal is called as the common mode rejection ratio. So always we will express the common mode rejection ratio in the case of operational amplifier is the ratio of differential gain to the common mode gain. So differential gain is nothing but whenever both the input voltages are different here, whenever V1 is not equal to V2, how much gain we are getting, that we are indicating with the differential gain. But if we are applying same voltages, V1 is equal to V2, common voltages we are applying, in that case how much gain we are getting, that we are calling it as the common mode gain. So the ratio of this differential gain to the common mode indicates the common mode rejection ratio of the operational amplifier. And in the ideal case this value is infinity, but in the practical case we will get it as large value. And next up, what is the need for frequency compensation in practical operational amplifiers? So here frequency compensation is needed in the operational amplifier when large bandwidth as well as lower closed loop gain is desired. Whenever we require bandwidth is high or large value and closed loop gain must be low. So to reach these particular conditions, we have to make the frequency compensation in the practical operational amplifier. So these compensating networks are also used to control the phase shift and also improve the stability of the system here. In most of the cases, these compensation elements we will add across the non-inverting terminal of the operational amplifier. Most of the cases we will utilize here it as the resistance, and that R compensation resistance almost equivalent to the input resistance of the operational amplifier. The next define slew rate. So slew rate is defined as the maximum rate of change of the output voltage caused by a step input voltage. That is nothing but if there is any small variations in the input voltage, how much amount of variation we are expecting across the output of the amplifier, indicating with the slew rate here. In the ideal case, the value of slew rate is infinite. Okay, op-amp's output voltage should change instantaneously in response to input step voltage. But in the practical case, we may not reach it as infinite value. So always we will indicate with here it as dV by dt or dV by dV naught by dVi. Next, what causes a slew rate? So here, because of the capacitor which is present in the output circuit of the operational amplifier, that is a cause for the slew rate in the operational amplifier. So this capacitor within or outside of the operational amplifier to prevent oscillation. So if it is this capacitor which prevents the output voltage from responding immediately to fast changing input here. So this actually the action of the capacitor is whenever we are providing the input voltage to the capacitor at that particular instant only, it will not respond or it will not charge here. So it will take some time to charge the capacitor. So because of that reason, it is affecting the slew rate in the operational amplifier. And next, defining integrated circuit or IC here. So here IC is nothing but some small size chip and it is very low cost device. It consists of IC consists of both the active as well as passive elements here. While coming to the passive elements, we can integrate on the IC or the resistor, capacitor, inductor, etc. are the passive elements. Along with these, we can also include the active elements like bipolar junction transistor or field effect transistor or operational amplifier. These all are the active devices. So both the combination of active and passive devices we can integrate on the IC to make it as particular application. And these integration of these components we are doing on this some small piece of semiconductor material. That material we can utilize here it as either germanium or silicon here. Depends upon our requirement, we can utilize either germanium or silicon semiconductor material to fabricate the integrated circuit here. And next, mention the advantages of integrated circuits. So the first advantage is the size of the IC is very less, and the equipment density will improve because of the less size, and the cost is also less due to batch processing. There is nothing but so many number of ICs at a time we can able to produce. Because of that, the cost will be reduces, and the functional performance of a device will be improved if we design with the ICs, and the speed of the device will also if we design with the ICs here. So that is nothing but cost, size is reducing here, and the speed is increasing and the performance is also increasing here. And one more basic thing, the power dissipation is also very less when we utilize the ICs instead of normal components which are designed on the printed circuit boards. And next, define power supply rejection ratio. So here this power supply rejection ratio, it is the ratio of changing input offset voltage, that is changing input offset voltage due to change in supply voltage. So if any variations in the supply voltage, there is some amount of variation in the input offset voltage of the operational amplifier, that we are indicating with the power supply rejection ratio. While performing this, the other voltage sources in the op-amp must be constant. And next, define inverting amplifier. So inverting amplifier is nothing but in which the output is given as feedback to the inverter terminal of the input of operational amplifier here. That is nothing but if we take one normal operational amplifier, this is having inverting terminal as well as non-inverting terminal 2, 3, and here it has the output terminal 6. It is 7 for one operational amplifier. Now it is in the open loop connection. We are not providing any feedback here. So it is the open loop inverting amplifier whenever we are providing the input to the inverting terminal and the non-inverting terminal is grounded. And this same inverting amplifier we can implement using feedback here. Using feedback resistance RF, I am connecting the some portion of output voltage back to the inverting terminal of the operational amplifier. So it is the closed loop inverting amplifier. It is the open loop inverting amplifier. So when we can say particular operational amplifier is inverting amplifier means when we apply the input signal to the inverting terminal so that it is the inverting amplifier. And in the case of inverting amplifier, always output is 180 degrees out of phase with the applied input signal. That may be in the open loop or in the closed loop. That is in the open loop configuration or in the closed loop configuration. And next, what is non-inverting amplifier? So in the case of non-inverting amplifier, the output is in phase with the applied input signal. Why? Because in the case of non-inverting amplifier, the input signal we will provide to the non-inverting terminal and the inverting terminal must be grounded here. So because of this reason, the output voltage in phase with the input voltage in the case of non-inverting amplifier. And also we can represent it with a feedback form or closed loop form by using the feedback resistance RF. And this one is grounded here. Here we'll measure the output voltage. So this is the open loop non-inverting amplifier, and this is the closed loop non-inverting amplifier. And next, to define amplification. So amplification means a process to increase the signal strength by means of amplitude. There is nothing but in the amplification, the amplitude of the signal will be increases, but not any variations in the frequency as well as phase angle of the signal here. That is main intention of amplification is to improve the amplitude of the signal or strengthen the applied signal here. And next, define summing amplifier. So the summing amplifier is one of the type of the operational amplifier. In this case, it is used to add or combine the different voltages applied across the operational amplifier. For example, I am taking the operational amplifier here, and for the inverting terminal, I am connecting 3 different voltages through the 3 different resistances here. So this is V1, V2, V3 voltages I am applying to the inverting terminal. So across the output, I'll get it as minus of V1 plus V2 plus V3. So this resistance values also we need to consider here. But what is the output we are getting? I am telling here. That is the inverse of V1 plus V2 plus V3. That is nothing. Why we are getting negative sign means I am applying the input voltages to the inverting terminal. So that's why minus of sum of all the applied voltages. Or else if we connect it to the non-inverting terminal means we will get the output is equal to sum of all the applied voltages. And next, define gain. So gain is the ratio of output parameter to the input parameter. That may be the voltage or current or power here. And next, define accuracy of the system. Accuracy can be defined as the amount of uncertainty in a measurement with respect to an absolute standard. That is nothing but when we design one particular circuit, we will define some ideal specifications. It should reach these particular values. It should provide this much voltage gain, and it should provide this much current gain. It should provide this much input impedance and output impedance. We will specify some values that may be the 0 or infinity. But in the practical case, we may not reach that specified ideal characteristics. So, how much variation we are getting in the practical case, that variation we are indicating with the accuracy of that particular system here. And next, define DC offset. So, DC offset is the unwanted DC output voltage which is appearing across the output of the operational amplifier along with the desired output signal. When we performing some particular operation in the operational amplifier, we should get the output of that particular application. But along with that, some amount of DC voltage also we are expecting in the practical case. That DC voltage we are calling it as the DC offset here. This is the undesired thing. Because of this, there is a variation in the output voltage. We will not get a exact or accurate result across the output. Next, what is voltage follower? Here, voltage follower is an electronic circuit which produces an output that follows the input voltage. Why here the output is following the input voltage means, in this case, always the feedback directly from output to input without any elements we are connecting output again back to the input here. So because of that reason, it is following the applied input voltage. In most of the cases, voltage follower we can utilize for the buffering purpose. And next, what is linear component? So any particular component which is obeying the Ohm's law, then we can call it as the linear component. And next, what is non-linear component? If any particular component which is not following the Ohm's law, that is R equal to V by I rule. If it is not following this means it is the non-linear component here. And always linear response means the proportionate response, whatever the input voltage we are providing, that corresponding variation of output voltage we can expect then it is the linear variation. Suppose output is not proportional to the input voltage, then we cannot say it as the linear. And next, define integrator. So here integrator is in one of the electronic circuit which produces the integration of the applied input signal to it. So in the case of operational amplifier, if we connect the resistance and in the feedback one capacitor, we can able to form the integrator circuit here. This is resistance, this is capacitance. So here we will get it as minus 1 by RCF integral of VA of dt here. So here RCF is nothing but the time constant of the circuit, and the time constant of the circuit always depends upon the how much resistance and how much capacitance we are utilizing to design this integrator circuit. And next, to define differentiator circuit. So here differentiator is also one of the electronic circuit which produces the differentiation of the applied input signal here. So in the case of op amp, we can able to design the differentiator. If we interchange the capacitor as well as resistor and the integrator, we can form the differentiator circuit. This is V0, that is, we will get it as minus d by dt of V in here into RCF. Again, RCF is the time constant of this differentiator circuit. And next, define biasing. So here biasing is the process of applying some external voltage in order to operate particular device in a desired way. So to get particular output from the device, we need to provide some external voltage. That voltage, we are calling it as the DC voltage or DC biasing. And next, what is the input impedance of a non-inverting amplifier? So the input impedance of a non-inverting amplifier is very high, that is almost infinity here, as the op amp draws negligible current from the signal source. It is nothing but if op amp draws no current in the input side, so because of that reason we are having infinite input impedance across the input of the operational amplifier. That may be in the non-inverting configuration or in the inverting configuration. And next, what is thermal drift? So here thermal drift is nothing but the changes in the normal operational behavior of the device due to the changes in the ambient temperature. It is nothing but because of the variation in the temperature, there is a variation in the circuit parameters, as well as there is a variation in the component values in the circuit. Because of that reason, the output voltage or output signal may vary here. So that process we are indicating with the thermal drift here. And next, what are the advantages of IC over discrete components? So the size of the IC is very less, first basic and main advantage, and the cost of IC also very less if we compare with the circuit design on the PCB. And the system reliability will be increases if we design with the ICs, and the functional performance of the system will also improve, and the speed of the system will improve, and the power consumption will be reduces. So these all are the advantages compared to the ICs, compared to the normal component circuits. And next, what are the different IC packages? So here we have 3 different IC packages. Those are metal can package designed with the metals, and ceramic flat package, and dual inline package. But nowadays we are utilizing this dual inline package, and our 741 operational amplifier is available in all the 3 packages. But in most of the cases, in most of the applications, we are utilizing only the dual inline package. Here we are having 1, 2, 3, 4, 5, 6, 7 and 8 pins. This is the 741 IC. Here we are having the notch to indicate the first pin of IC. So in this way we need to count the IC numbers 1, 2, 3, 4, and then in this direction 5, 6, 7, 8. So this is the dual inline package of the 741 operational amplifier. And next, what are the ideal characteristics of operational amplifier? So the ideal characteristics of the operational amplifier are voltage gain is infinity and input impedance is infinity, output impedance is 0 and bandwidth also infinity and offset is 0 and the slew rate is also infinity and common mode rejection ratio is also infinity in the case of ideal operational amplifier. And next, define input offset current. So input offset current we are indicating with IIOS. So it is the difference of the currents which are flowing in the inverting as well as non-inverting terminals of the operational amplifier, that is IB1 minus IB2. So this is the input offset voltage of the operational amplifier. And next, define common mode rejection ratio of the op-amp. It is a different signal as compared to a common mode signal is called the common mode rejection ratio, CMRR. So mostly we will indicate with the ratio of differential gain to common mode gain in the operational amplifier. And next, why IC741 is not used for high frequency applications. So here in the case of IC741, it is having low slew rate because of the predominance of the capacitance which is present in the circuit at high frequencies. So as frequency increases, the output gets distorted due to the limited slew rate. So because of that reason, we are not utilizing for the high frequency applications. And why does an op-amp have high common mode rejection ratio? So here high common mode rejection ratio ensure that the common mode signals such as noise are rejected successfully and the output voltage is proportional only to the differential input voltage. That is nothing but in this particular condition, the op-amp can able to amplify the applied differential input signal only. It will not amplify the noise signal and it will not provide any noise or distortion across the output of the op-amp. And next up, what is the classification of ICs based on complexity level? So here are different types of classification is there. That is small scale integration, SSI. And next, medium scale integration and large scale integration and very large scale integration. Nowadays, we are utilizing the very large scale integration ICs. So here these ICs are classified based on how many number of components are integrated on the ICs. That indicates the different types of integrations here. And next, what is the classification of ICs based on the fabrication process? So here two types of ICs are designed here based upon the fabrication, that is monolithic ICs as well as hybrid ICs. And next, what produces more offset voltage at the output? The input bias current which is present at the input terminals of the operational amplifier will produces more offset voltages across the output of the operational amplifier. And what are the typical values for an IC741 operational amplifier? So the input bias current is 500 nanoamperes and input offset current is 200 nanoamperes and input offset voltage is 500 millivolts. These values are for the practical IC741. But in the ideal case, these all values must be zeros here. In the practical case, we should not get any offset values here or offset voltages here. And next, define power supply rejection ratio. So here it is defined as ratio of change in input offset voltage to the change in supply voltage by keeping other supply voltage as constant. That indicates the supply rejection ratio here. And next, what are the factors that changes op-amp parameters? So here by if the temperature varies, the parameters of the operational amplifier also varies here. And if we change any input supply voltage also, there is a variation in the output parameter. And due to the time variations also, we may get different output voltages across the op amp here. And next, define differential amplifier. So the differential amplifier is one of the electronic amplifier which will amplify the difference of the two input voltages which are provided across the two input terminals of the differential amplifiers, and it will suppress any common voltages which were provided to the two input terminals of the differential amplifier. In the case of differential amplifier, we are having two inputs, but the two inputs will provide the two different voltages. So the difference of the two applied voltages, it will amplify here. And next, what are the different types of differential amplifier here? So here 4 types of differential amplifiers are there. Depends upon how many number of inputs we are utilizing and at what way we are measuring the output across the differential amplifier. By considering the two parameters, we divided it as 4 types. Okay, that is dual input, balanced output differential amplifier. So in the case of our differential amplifier, we are having two similar transistors, the two identical characteristics, and those are having similar emitter resistances or same emitter resistances, and also the collector resistances are also same, and we will provide the common supply. So here it is minus VE, and here we will provide the V1 and V2, two supply voltages or two input signals for the two transistors. So dual input balanced output differential amplifier means we are utilizing two inputs for the two transistors and we'll measure the output across the common point of two collector terminals of the differential amplifier so that it is the balanced output. And next, dual input unbalanced output differential amplifier means in this case we will utilize both the V1 and V2 voltages, but the output will measure either across collector of the Q1 transistor or collector of the Q2 transistor. Across any one of the collector of the transistors, we will measure the output signal. And next, single input balanced output differential amplifier. Single input means either we will utilize V1 or V2 only, not at a time both. And balanced output means again we will measure across the common point of both the collector terminals. And next, single input unbalanced output differential amplifier means again in this case also we will utilize either V1 or V2 voltage, but the output will measure either Q1 collector or Q2 collector across first transistor collector or second transistor collector. We will measure the output. So based upon these 4 types of differential amplifiers will work here. And next, give the gain formula of inverting amplifier. So in the case of inverting amplifier, we are having the open loop inverting amplifier. In the case of open loop inverting amplifier, we will provide the input signal to the inverting terminal and the non-inverting terminal is grounded and the output will measure here. So the output voltage is minus of gain times the input voltage in the case of open loop op amp. And similarly, if you take the closed loop inverting operational amplifier, we are having R1 and RF resistance here, and this is grounded. It is V0. So in this case, the output voltage is minus closed loop times the RF by R1 times the VA here. Okay, so here we can write the gain, the closed loop gain is equal to minus RF by RA or R1 in the case of inverting operational amplifier, and always 180 degrees phase shift we will get in the inverting operational amplifier. And next, give the gain formula of non-inverting amplifier. So in the case of non-inverting amplifier, if we take the open loop configuration, the input signal we will provide to the non-inverting terminal, and this must be grounded, and here we'll measure the output voltage. So in this case, the output voltage is gain times the input voltage. So the open loop gain is the ratio of output voltage to input voltage. In this case, the output voltage is in phase with the input voltage. And if we take this is in the case of open loop, and similarly if we take the closed loop configuration, RF and R1 resistance, and here we are applying the input signal, and this one is grounded, and here we'll measure the output signal. So in this case, we will get the gain equal to 1 plus RF by R1 times. This is the closed loop gain of the non-inverting operational amplifier. This is the open loop gain. And next, what is square wave generator? So the square wave generator is one of the electronic circuit. Again, it is able to generate the square wave signal. By using operational amplifier, we can able to implement the square wave signal here. So in this case, we are not providing any input signal to the square wave generator. So it acts like some multi-vibrator circuit. So it will provide the output without application of the any AC signal. By using the supply voltage only, it will provide the signal. And next, what is triangular wave generator? So the function of the triangular wave generator is to generate the triangular wave signal. So here this triangular wave generator, by using the square wave generator as well as by using the integrator circuit, we can implement this. These both circuits are again designed with the op-amp only. So here from the square wave generator, we will get the square wave signal. That square wave signal, if we apply it to the integrator circuit, we will get the triangular wave across the output. And next, what are the applications of triangular wave generator? So these can be utilized for sampling circuits and thyristor firing circuits, for frequency generations, and for tone generation circuits we can utilize this. And next, what are the applications of square wave generator? So the square wave generator in most of the cases, in order to provide the timing signals for different processors and controllers, and in any audio and radio applications, and in most of the cases we will utilize the square wave generator. And next, to mention the frequency of oscillation of a square wave generator. So here in the square wave generator, we are utilizing the comparator circuit. So depends upon the two input levels, it will give the output as either positive saturation or negative saturation, and it will reach us to either upper threshold voltage or lower threshold voltage of the signal. So by considering all into consideration, we will get the frequency of one oscillation of the square wave generator as 1 by 2 RFC ln plus V saturation minus lower threshold voltage divided by positive saturation minus upper threshold voltage. Here RFC we are going to utilize in the comparator circuit. And next, mention the frequency of oscillation of triangular wave generator. So this triangular wave generator is implemented along with the operational amplifier with 3 resistances, R1, R2 and R3 resistances and 1 capacitor. So that's why this value is R3 by 4 R1 C1 into R2. And next, what is comparator? So here comparator is an electronic circuit which compares the two input signals which are applying to it, and it produces the output. So the output may be either greater or lesser compared to the another one. So this comparator will comes under the linear applications of the operational amplifiers, and this comparator is also available in the inverting mode as well as the non-inverting mode. And here depending upon the inverting and non-inverting mode, we will get the output as either positive saturation or negative saturation, depends upon which amount of inputs we are providing across the two input terminals of the comparator circuit. So in this session, we discuss the different definitions as well as terminologies which are utilized in the operational amplifier. circuits and its applications. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.